What is up, guys? Welcome to the exam 2 review video. And in this video I'm gonna review all the topics that are important for your exam 2. And there's also a bonus content on this video. So I've recorded a full lecture video on the horizontal curves that you can watch in this video. And to make it easy for you guys to navigate, I've added a timestamp of all the topics that I'm going to cover in this video. So go to the description section on your YouTube and you can directly click on the topic that you are interested in. But I recommend you to watch the entire video from the beginning because I'm going to discuss a lot of important concepts as well as it's going to be interesting. So let's get started. All right, so let us first learn the concepts of the azimuths and bearings, which are very, very important in the traverse surveying. Whenever you draw a line in a surveying, we use a system called the whole circle bearing to represent the direction of that line. So imagine a circle like this and divide this into 4 quarters. Now I use these points to represent my north, south, east, and west direction. So this is north, south, and this is my east, and this is my west. And the angle at here at the north is 0 degree, and when you reach east it is 90 degrees. So at south it is 180 degree, and west is 270 degrees. And when you make one complete rotation like this, you'd end up getting 360 degrees right here. Okay, so this is called the whole circle bearing system, which is used to represent the direction of lines in the traverse. So what do you mean by the azimuth? So azimuth is the angle measured clockwise from the north. Okay, so if you take this line AB, so the azimuth of this line would be the angle measured clockwise from the north. So this angle is the azimuth of this line. So let's say we have another line right here. So what is the azimuth of this line? So you draw this angle clockwise from the north. So this angle would be the azimuth of this green line. So for this quadrant, the azimuth of this blue line would be the angle measured clockwise from the north. And you can see that I'm starting from the north and I'm ending right on this line. So this angle is the azimuth of this blue line. And lastly, for this orange line, drawing the angle measured clockwise from the north. So this angle would be the azimuth of this orange line. So this is how we show the azimuth of the lines in the traverse. So another way of representing the direction of line is through the bearing. So bearing are the acute angles measured either from north or south. And unlike the azimuth, which are the angle measured clockwise from the north, right? You always measure the azimuth clockwise from the north. Whereas in bearing, you measure the direction of the line either from north or from south. Okay, so it's either measured from north like this, so towards the east, or if it is towards the west, measure the angle from this north, or either you measure the direction from the south. So you always measure angle like this for the bearing. Okay, like this. So let's say this is 20 degree. So how do you represent the bearing? So what you do is you first write this N right here. So the angle from the north is 20 degree. So it is pointing towards the east. So my bearing of this line would be north 20 east. Okay. So for this line, so you first write south because it is pointing towards the south. And let's say this is 30 degree. So the angle from south to this line is 30 degrees. So it is south 30. And this line is pointing towards east, so your last letter would be east. So for this line, the first letters would be south, since this line is pointing towards the south, and the angle of this line from the south is, so let's say it is 20 degrees, so your angle would be 20, and this line is pointing towards the west, so south 20 west would be the bearing of this line. And lastly, for this line, I think you might have guessed it by now, the first letter would be north. So let's say this angle is maybe 30 degrees, okay, any random value, so north 30, and this line is pointing towards west, so your last digit or your last letter would be west. So this is how you represent the bearing of any given line. Okay, you either measure it from north or you measure it from south, You first write either north or south, then you write the angle, and then you write east or west, depending on whether this line is pointing towards the east or towards the west. So this is the concept of the bearing. All right, so let's learn how to convert from azimuth to bearing and vice versa. So I'm going to provide you with the explanation of the homework problem that I gave it to you. So this was the first the homework problem, and the question here was to convert from bearing to the azimuth. And let me show you how to solve this. So the first step is step number 1 is to draw the sketch. Okay, so let me try to solve these two problems simultaneously. So the first one is north, this angle west. So let me write here north, south, east and west, 0, 90, 180 and 270 degrees. So northwest, so should be my line. So this is my angle, 80, 40, 20. Okay, so we need to find the azimuth of this line. So like I said in the previous slide, the azimuth of this line would be the angle measured clockwise from the north. So I need to find this angle. So how do I find this angle? So I told you, right? So one complete rotation is equal to 360 degrees. So if you make one full turn from here till here, it is 360 degrees, right? So in 360 degrees, this part is 80, right? So how do you find this remaining part? You simply use this 360 degree minus 80, 40 and 20 minutes. So if you do this, you try to solve this, 360 degree minus 80, 40 and 20, so 279 degree, 19 minute and 40 seconds. So this would be the azimuth of this line. So let's try this second one. South 15 degree, 50 minutes and 10 seconds east. So my line would be north, south, east and west. So this would be my line like this, and my angle would be this angle, 15, 50 and 10. So what is the azimuth of this line? Again, azimuth is the angle measured clockwise from the north. So I need to find this angle. So what is the value of this angle? Again, this is 0, right? This is 90, this is 180, this is 270. So out of 180 degree value, so this is 15, right? And this whole angle from here to here is 180 degree. So what is this value, right? What is this angle? Well, what you do is you simply subtract 100 degree. Let me erase this. Subtract this angle from 180 degree, so 50, 10 seconds, and if you do that, then you get 164 degree, 9 minute and 50 seconds. So this is the azimuth of this line given the bearing. So this is how we convert bearing to azimuth. Alright, so let us convert the azimuth to bearing. And again, the step number 1 is draw the sketch. And step number 2 is, well, there is no step number 2. There's just step 1, which is draw the sketch. Okay, so let's try to convert this to bearing. So first you draw this, right? North, south, east, and west. So how do you show this angle in azimuths? So again, 0, 90, 180, 270. So 120 degrees would be this line, and this angle would be 120 degree, 15 minutes and 25 seconds. So what is the bearing of line? I told you to ask these 3 questions: north or south. So this line is pointing towards south, right? So it is south. So what is angle from south? So if it was pointing towards north, then this would be angle from north, but it's pointing towards south. So what is this angle? So again, I told you, right? This angle from here till here is 180 degree, right? And so this part is 120. So what is the remaining part? Well, you subtract this angle from 180 degree. Okay, let's try to solve this visually, okay? So 180 minus 120, 15, 25, and that would give you 59, 44, 35. So this angle is 59, 44, 35. So bearing of this line would be north, right? Sorry, south. This angle, and it is pointing towards east. So east. So this would be my bearing for this line. Okay. So let's try to solve this one. And again, now I think you guys are comfortable with this. So 275 degree would be this line, and the azimuth of this line would be this big angle, would be my azimuth. So I need to find the bearing of this line. So it is pointing towards the north. So my first letter would be north, right? And it is pointing towards the west. So it is definitely, it is west. So I need to find this angle, right? Because we're measuring the angle from the north. And how do you find this angle? Well, one complete rotation is 360 degrees. So simply subtract this angle from 360 degree, and solve this. 360 minus 275 degree, 30 minutes and 20 seconds. So that will give you 84, 29 and 40 for this line. And for first one, it is south, 59, 44, 35. Yes. So this is how we convert azimuth to bearing, and the key here is the sketch, right? If you know how to draw the sketch and if you understand the concept, then you can easily convert from azimuth to bearing and bearing to azimuth. All right, so let's learn how to do the angle adjustment in the traverse. Well, this is one of the easiest and the simplest topic in the traverse, but I don't get it why some of you are still confused with this. I even posted a video explaining the homework problem related to this video, but I want you guys to use your common sense in this topic and not repeat the same mistake. So let's clear the confusion. So while this equation may look very, very simple to you, this equation is the most important part in solving the problems related to the angle adjustment. And I've said this repeatedly, the sum of the interior angles of the polygon is given by n minus 2 times 180 degree, where n is the number of sides of a polygon. So if I give you a traverse like this and tell you to find the sum of the interior angles of this polygon, so you simply use this formula, right? N minus 2 by 180 degree, where n is the number of sides of the polygon. So if I give you like this kind of traverse having maybe a million sites. Well, that kind of traverse is not possible, but let's say I give you a traverse with a million sites, then still you can calculate the sum of the interior angles of this traverse by applying this equation. Okay, so make sure you understand how to use this equation. So why do we need to adjust the angles? So let's take an example of the simple traverse, which is a three-sided traverse, and all the angles are 60 degrees. So if we add this, right, 60 times 3 is 180 degree. And if you apply this equation, n minus 2 times 180 degree, so 3 minus 2 times 180 degree will give you 180 degree, right? So this is a perfect traverse. So imagine what happens if you measure one of the angles as 100 degree instead of 60, right? So let's say you made some mistake and you measure this angle as 100 degrees. So 100 plus 60 is 220, right? So it is not equal to 180 degree, and you can't get a triangle whose sum of interior angle is 220 degree, right? So let's see what happens when you measure it 100 degrees visually. So if this is 100 degree, then your third side would be like this, and you can see that this traverse is not closing, right? It should form like a closed polygon, but since you measure one of the angles incorrectly, the traverse is not closing. So that is why we need to adjust the angles so that we can close the traverse. Alright, so let us try to solve this problem. So here you're given a traverse with all the interior angles, and you need to find two things. The first one is the adjustment or the correction factor, okay? And the second one is adjusted value, okay? This is also called the final value. So I see some of you are confused between two terms. So adjustment means the correction factor that you'd apply to each of these angles, and adjusted means like what is the final angle after you apply the correction. Okay, so make sure you don't get confused between these two terms. So let's try to solve this step by step, and I want you guys to follow the steps, okay, because these numericals need to be performed very systematically. So step one is you find the actual sum, right? So how do you find the actual sum? Well, you add all the angles. You add all these angles, right? So angle A plus angle B plus angle C plus angle D. So if you add all these angles, then you'd get 360 degree, 12 minute and 00 seconds. So this is my actual sum, right? Step number two, you find the theoretical sum. Guys, follow the step-by-step process, because if you follow the step-by-step process, then you never make the mistake. So how do you find the theoretical sum? You use this equation, n minus 2 times 180 degree, right? So here the number of sides is 4. So 1, 2, 3, and 4. So 4 minus 2 times 180 degree, and that would give you 360 degrees is my actual sum. So guys, imagine that if I give you a traverse like this, this kind of traverse, very fancy traverse, and if I tell you to find the theoretical sum, so don't get confused like we have never studied a diagram like this. Well, it doesn't matter, just apply this equation, n minus 2 times 180 degree, and count the number of sides. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. It has 17 sides, right? So use n equals to 17, and then you find the theoretical sum. Okay, so our third step is to find the error. So what is error? So error is given by actual sum minus theoretical sum, right? So our actual was 360, 12, minus the theoretical sum is 360. So if you subtract this, you get 12 minutes, right? So this is my error. And guys, remember the sign of the error, right? Actual minus theoretical. So here our sign is positive. Sign is positive here because this is very, very important. Okay, and again, use this strategy. If the error is positive, then your correction would be negative. And if the error is negative, then your correction would be positive, right? So here you can see that our error is positive, so our correction would be negative. Should be negative value, right? Some value, but the sign would be negative. So how do you divide the error? This is step number 4. Is try to divide the error equally, right? Uniformly among all the angles. So here the correction would be the error, if you divide this by the number of angles, right? So 12 divided by 4 equals to 3, right? And note that, so it doesn't have decimals, right? It does not have decimals. And I've said that we always use the whole number as a correction factor. We never use decimals, okay? So if it doesn't have the decimal, simply use this value, okay? So the correction factor for each of these angles would be 3. Why is it 3? Because this 12 is divisible by 4, right? Or the number of angles, and you are getting this number, and we don't have any decimals, so just divide the error equally. That's it. So in the next slide, I'm going to explain what happens if you get the decimals, but this is the first condition, right? So your angle is, let me write the angle. Angle A is 61.4200. So if you subtract this 3 from here, then what would be the final angle? So try to subtract this. 61.4200 minus 3 minutes should be 3 minutes of error. I'll try to solve this. Right. So this would be 61.3900. My second angle B is 110.10.00. So I subtract 3. So 110.10 subtract 3 minutes. That will give you 110, 7 minutes and 00 seconds. So angle C is 54.15.00. So 54.15.00. Subtract 3, and that gives you 54.12.00. And D is 134.5.00. So subtract 3, and that will give you 134 5 minutes and 00 seconds minus 3 and 0. And that will give you 134.200. And guys, one of the advantages of, or one of the best things about this problem is that you can check the answers by yourself, because now you found the final values, right? And if you add all this, then you should get 360 degrees, right? So try adding all these values. So in the exam, just spend some time checking your answers. Don't just solve it and submit your work. Just try to check it, recheck it, because we are humans and we make mistakes, right? But we need to double check our work and make sure that our work is mistake proof. So if I add all the angles, then I get 360 degrees, and that is how I make sure that my corrections are valid or mathematically correct. So this is how you adjust the angles. when the error is divisible by the number of angles and when you don't have any decimals. Okay. So let's see another case when you get some decimals in your correction factor. So let us see the second scenario. So case number 2, when your error has a decimal. Okay, so there are like two conditions. So I want you guys to understand both of these conditions. So let us change the value of one of the angles. So let's make this 43. So I've increased 1 minute. So if I do this, then your actual sum becomes 360 degree 13 minute 00 seconds, and it's 13 because I've increased one of the angles by 1 minute. So let's make it 13. So your theoretical sum would be 360 degree, and here our error is a minus t, and that will give you 13 minutes, right? So let's try to find the adjustment. So I told you, right, adjustment, we divide this error by the number of angles. So 13 by 4 would give you 3.25 minutes. And you can see that it has decimals, right? So we can't use the method that I showed you previously. So we can't use this 3.25, 3.25, 3.25, and 3.25. So we can't use this because we only use a whole number as a correction factor. And the reason is because when you tune in the total station, then you can't tune in like decimals of seconds, right? You can only tune in your whole number. So that's why we can't use decimals. So we don't use this. So what's the method here? Here the technique here is try to divide the error as equally as possible and assign the remaining value to the larger angle. So find the larger angle here. So you find the largest angle. So here in this case, this should be my largest angle, right? So what you do is you simply take this 3.25. So use this first number next to the decimal. So minus 3, minus 3, minus 3, right? So minus 3 times 3 equals to minus 9. So what's the remaining error? So 13 minus 9 is 4, right? So this allocate the remaining error or the larger error to the largest angle. It is because when you try to measure the large angle, right? You're trying to measure a large angle, there's more chance that you'd make mistake because the angle is large. That is why we assign the largest or the remaining error to the large angle. So this is how I do the correction: minus 3, minus 3, minus 3, and minus 4. And the reason why it is like this is because we are getting this decimal point, and that is why we can't divide the error equally like we did in the previous case. So this is how you do it. Okay, so I want you guys to use your common sense about why we are doing this and why it should be equal in some cases, whereas it should be like this in other cases. Alright, so in the beginning of this video, I explained you the concept of the traverse, and now we are going to apply the same concept to find the azimuth of the traverse line. Okay, so if I tell you to draw a line AB of length 20 foot, whose azimuth is 45 degrees, how do you sketch that line? And azimuth is important in traverse because I told you, right, a line has a length and a line has a direction, because a line can point anywhere. So if you just specify a length to a line in traverse, then it would be quite vague. So we need to assign a direction as well. So what you do is you first start with the first point, okay? And let's call this A. And I want you guys to use this compass, okay? So whenever you draw a line in a traverse, always use this compass because it makes your life so easy. So azimuth of this line is 45 degrees, so I draw this line 45 degrees from north. and this would give me my second point B, and I place this compass here. So this length is equal to 20 foot. Okay, so the azimuth of AB is 45 degrees, and it means that you are walking from A towards B. So this is how I want you guys to visualize the azimuth. Okay, so I want to go from A to B, so I have to walk 45 degrees from north like this, and this is what the azimuth is telling me. So what is the azimuth of the line from B to A? Okay, so what is the azimuth of this line BA? So the azimuth of AB is not equal to the azimuth of BA, okay, because it depends on the point of reference. So if I tell you to find the azimuth from B to A, then you should be finding this angle, right? From B to A, the azimuth would be this angle, okay? And it means that the azimuth from B to A, it means that you are walking from B to A. So if I have to walk from B to A, then I have to walk at this angle, measure clockwise from the north, right? I can't walk at an angle of 45 degrees, because if I walk at an angle of 45 degrees, then you'd never reach point A, right? So this is how I want you guys to visualize the azimuth. So what is the value of this? To find the value of this, it is very, very easy. Okay, so if this is 45 degree, then this angle is also equal to 45 degree. So in geometry, if you have this two parallel lines, and if this angle is x, then this angle would also be x. So I'm trying to give you some free geometry tips here. And the angle from here to here is 180 degree, right? So what would be the angle from here to here, which is the azimuth? So aren't you simply supposed to add 180 degree to the forward azimuth? And that will give you 225 degree. Okay, so the azimuth of A to B is also called the forward azimuth. Okay, so why is it forward? Because you are moving from this point to this point, right? You are moving forward. And the azimuth of B to A is also called as the backward azimuth. Okay, backward azimuth. So backward azimuth equals to forward azimuth plus 180 degree. So this is the equation that we use to find the backward azimuth of a line. So the forward azimuth means that you are walking from A to B, right? And the backward means that you are walking backward from B to A. So this is the concept of the azimuths of a traverse line. So let us try to recall the example that we did in the class. So here I have a very, very simple three-sided traverse, A, B, and C. Okay, and so let's say all the angles are 60 degrees, which means that it is an equilateral triangle. And again, like I said, right, whenever you draw the traverse, you just use this compass sign on the vertex of the traverse, because it makes your life so easy. And let's say the azimuth of the line AB is 45 degrees. Okay, it is given to you. Usually the azimuth of one of the lines of the traverse will be provided to you, and you need to find the azimuth of the remaining lines. And also, if you were present in the lab, you computed the azimuth of one of the lines, right, in the oval. So your traverse was something like this, and I made you guys to measure the azimuth of one of the sides, and you measure that, right? So we have to measure the azimuth of one of the sides, and using that we'll find the unknown azimuths, okay, or the azimuths of the remaining sides. So it is 45 degrees, and again I want you guys to go clockwise. Okay, so if the azimuth of the line AB is provided to you, then you go clockwise like this. Okay, so basically you are walking from A to B, right? The azimuth of AB is 45 degrees. You are walking from A to B. And And then from A you'll reach point B. So from point B you are walking towards point C, right? So what dictates this walk is this direction, right, which is the azimuth of the line BC. So how do we find the azimuth of BC? Well, we use this equation. So the azimuth of BC is given by previous azimuth plus at 180 degree, and you subtract the interior angle at B. Okay, I see that most of the students are confused with what angle to take. Well, you always take the interior angle at the starting point of the line. Here the starting point is B, so I'm taking the interior angle at this point B. Or you can also say this as it is, as like this. So you take the angle of the line whose azimuth is known, right, with the line whose azimuth is unknown. So this is known, this is unknown, right? So known to unknown, right? You find the angle between the line whose azimuth is known, the point to the line whose azimuth is unknown, right? So here 45 degree is the previous line plus 180 degree minus the angle at B is 60. So if you do that, then you get 165 degree. So the azimuth of BC is 165 degrees. So you reach point C like this, and from C you are walking towards A, right? So imagine, so what is dictating this direction? So what is determining this direction is this angle, right? If this guy knows what is this angle, then he can walk towards A, right? And this angle is called the azimuth. So what is the azimuth of the line CA? It's the same formula. So previous azimuth plus 180 degree minus the interior angle, right? So interior angle where? At this corner C, because the starting point of the line CA is C, right? This is the starting point. Or you can even do like this. So this azimuth is known, right? Known line versus the unknown line. And if you do this, then 165 plus 180 minus 60 gives you 265. The azimuth of CA is 285 degrees. And remember one thing, azimuth can't be, okay? Azimuth can't be greater than 360. Because imagine this, can you have an azimuth greater than 360 degree? Because one complete turn is equal to 360 degree, right? So azimuth cannot be greater than 360 degree. If it is greater than 360 degree, then you need to subtract 360 degree. Okay, so if your azimuth is 400 degrees, then you can't have an azimuth of value 400 degrees. So what you need to do is subtract 360 degree, and that will give you your azimuth. Okay. All right, so here I'm going to explain the homework problem to you, and most of you did pretty well, but still some of you are confused. I'm making you solve it in the class, but still you're making mistakes. But let's clear the confusion. So first I want you guys to visualize the figure. Okay, so this was a figure that was provided to you. So it is a 1 2 3 4-sided traverse. So A, B, C, and D are the vertex, and these are the angles. So these are the angles, right? Angle at each of these vertex, and the length of each of these traverse lines are provided to you. And note that the azimuth, right? The azimuth A dash B, which means that the azimuth from A to B is provided to you, and which is 338.300 degrees. Okay, it is in decimal degrees, which is a good thing. So here you need to find the azimuth of the remaining lines. So what is the azimuth of BC, the azimuth of CD, and the azimuth of AD? So how do you find the azimuth of the remaining sides is the question, right? And I always tell you to go clockwise, right? So the azimuth of AB is provided to you. So the azimuth of A to B is provided to you. So you go clockwise like this. Okay, you go clockwise, and the equation that we are going to use is simply azimuth of previous line plus 180 degree minus the interior angle to the line from known azimuth to the unknown azimuth, which is simply this angle, or you can say that the angle at the starting point of the line. Okay, and also this can be written as the angle at starting point of the line. So this is how you compute the azimuths. So here in this question, let's try to find the azimuth of all the remaining lines whose azimuth is unknown. So here the azimuth of the line AB is known, which is 338.30. So you need to find the azimuth of the remaining line. So let's try to find the azimuth of BC. So azimuth of BC. So the equation is you take the previous azimuth, right? 180 degree minus the interior angle at dash dash dash. So most students get confused here, so they don't know which angle to take. So you're trying to find the azimuth of the line BC, right? So what is the starting point of the line BC? The starting point is B, right? So you take the angle at B. So the angle at B is 75. So you take angle at B, which is 75. So my previous azimuth is 338.30 plus 180 degree minus 75. And if you do this, then you get and you get 443.3. And some students are just writing this value, but I said that azimuth can't be, so azimuth can't be greater than 360 degree, right? Because you can visualize it this way. So one whole turn is 360 degrees. So how can the azimuth be more than 360 degree? So when the azimuth is more than 360 degrees, just subtract 360 degree from that value. Okay, so here this minus 360 would give you 83.3, right? So the azimuth of BC would be 83.30 degrees. Okay, so what's the azimuth of CD? Again, previous azimuth plus 180 degree minus angle at. So the starting point of the line CD, right? The starting point of the line CD is C. So you take the angle at C. Okay, angle at C, and that would give you, so previous would be 83.3 plus 180 degree minus the angle at C is 142.589. Do this. That will give you 120.711. So this would be 120.711. So what is the azimuth of the line DA? So azimuth of DA, which is going to be this line, and again use the same equation. So previous azimuth plus 180 degree minus the interior angle at. So we're trying to find the azimuth of DA. So the starting point is D, right? Starting point is D. So you take the angle at D, which is 44.161. So the previous azimuth is 120.711 plus 180 degree minus the angle at D is 44.161. So if you solve this, then you get 711 180 minus, then you get 256.55 degree, right? So 256.55 degrees. And lastly, we'll check if our work is correct or not. Okay, we'll try to find the azimuth of AB, right? So we went from D to A, and now we will go from A to B. So the azimuth of AB is given to you, so we'll try to check, okay? Using this equation, we'll try to find the azimuth of the line AB, and if it matches with this, then our process is correct, okay? So what is the azimuth of AB? So you take the previous azimuth plus 180 degree minus the angle at A, right? Interior angle at A. So my previous azimuth is 256.55 plus 180 degree minus the angle at A is 98.25, right? So if I solve this, then I get 338.30, and you can see that this value matches with the azimuth that is provided in the question. So I want you guys to check. So always check the azimuth of the first line. So you start from here, right? Start from here and you go all the way till here and just check the azimuth of the first line using this equation, and if it matches with the azimuth that is given in the question, then your process is correct. If it is not equal, then you made some mistake. Okay, so make sure you check your work. This is how you find the azimuths. Okay, next let us learn the concept of the latitude and departure, and take note that these are the unadjusted values. So in the next topic we'll learn how to adjust the latitude. So if we take this line AB, whose azimuth is 40 degrees and length is L, so let me try to extend this lines, north and north, south and east west lines. So you can see that these lines intersect at this point and it is a right angle triangle, right? So latitude of a line is the vertical projection of a line. Okay, this is the line and its length is L. So this distance or this length is called the latitude, which is the vertical projection of a line, and this is called the departure, which is the horizontal projection of a line. So these are the latitude and departure of a line. So each line or every line will have a latitude and a departure. Okay, so how do we find the latitude? So the latitude of a line is given by the length times the cos of bearing. Okay, so latitude equals to length times the cos of the azimuth. Okay, so let us say the length of AB is 1000 foot. So the latitude is given by 1000 times the cos of 40, which is the azimuth, and then you get 766.044 foot. And departure is given by, so departure is given by the length times the sine of the azimuth. Okay, so here you can see that departure is 1000 times the sine of 40, and that would give you 642.788. Okay, and this is a pretty simple and straightforward formula, but what I've seen is that some people are still using radians in their calculator, which is incorrect. I'm tired of telling you that you always use degrees because our angles are in degrees. You never use the radians, you never use any other units of measurement. You always double check that your calculator is set to degrees. Okay, all right. And guys, latitude and departure can be positive or negative. It is because when you apply this formula, length times the cos of the azimuth, or the length times the sine of the azimuth, then your answer can be either positive or negative. So how do you know what positive means and how do you know what negative means, right? So these are the sign conventions that we use. So if you get a positive value in your latitude, then it means that you are moving towards the north, or your point is towards the north relative to you, okay, or you are moving towards the north. If your latitude is negative, then you are moving towards the south. If your departure is positive, then you are moving towards the east. And if your departure is negative, then you are moving towards the west. So this is what this sign conventions tells you. Okay, so latitude can be positive or negative. So positive means north, negative means south. And again, departure can be positive or negative. So positive means east, negative means west. Okay, so this is how we classify the latitude and departure into plus and minus into their respective directions. All right, so let's try to find the latitude and departure of these lines, and make sure you read your questions properly, because here you have been told that to use at least 6 decimal places. Okay, so read the question. So how do we find the latitude? Again, latitude equals to length times the cos of the azimuth. So guys, length and the distance are the same thing. Okay, so this distance means length. So for this line AB, so the latitude would be length, so 500, right, times the cos of the azimuth. So the azimuth of the AB is 338.30. So if you do this, then you get something like 464.566 2858, right? Or you can round it up to 6 decimals. 286. 56628 You round it up to 6 decimals, right? So this would be my latitude. And since this is positive, so I write this on the north column, right? It is positive, so I write it right here, the northern part. So plus 464.566 286. Okay, so what is the departure of the line AB? So the departure is given by length times the sine of the azimuth, right? So length is 500 times sine of the azimuth, which is 338.30. So if you do this, then you get 500 times sine of 338.30, and that gives you negative of 184.873379, right? So departure is negative, so minus 184.873379. Okay, and make sure you write the sign. Okay, if you don't write the sign, then you might end up doing a mistake. So make sure you keep the sign intact when you write down the values. Okay, so let's try to find the the latitude of BC. Okay, so again, for this line BC, so my latitude would be length, right? So the length of BC is 475. So 475 times the cos of my azimuth. So the azimuth of B is, let me write down the azimuth that I computed in the previous step. So 83.30, 120.711, and DA was 256.55. So this is my azimuths. So the cos of azimuth of BC 83.3. So if I do this, get 475 times the cos of 83.3, that will give you 55.418600. So it is positive, right? It's positive, so I write like this, positive 55.41 8600. So what is the departure? So departure equals to length 475 times the sine. So the only thing that is changing is either sine or cos. So 475 minus the sine of 83.3, that will give you plus 471.756 059. So again, it is positive. So I'm writing here in this column 471.756059. Okay. So let's try to find the latitude and departure for line CD. So let's do it for the line CD. So my latitude is length, right? So what is the length? Is this 630 times the cos of the azimuth, 120.711, and this gives you negative, right? You're getting negative 321.746 033. So it will be here negative of 321.746033 would be my latitude. So my departure is length, which is 360 times the sine of 120.711, and that would be plus 541.645170. So it is positive. So plus 541.645170. All right. So let's find the latitude and departure of our last line. So for DA, latitude would be length, which is this value, times the cos of the azimuth, which is 256.55, and that would give you negative 198.172407. So I'll write it right here. It's negative 198.172407 is my latitude, and my departure is again length, this value, sine of 0.55, and that will give me 256.55, give me negative 828.6324. Sorry for that glitch. So this would be 828.63 2426. So I write it right here, negative, right? So it's negative, so negative 828.632426. So this is how I calculate the latitude and departure of all the lines using the equations. So your next problem was, how do we find the latitude closure error? Well, to find the lat closure error, all you need to do is add all this latitude and add all the departure. And when I tell you to add the latitude, just keep the sign as it is. And that is why I tell you to write the sign, right? So this would be 464.566 plus 55 point dash 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 minus 321 and minus 198.17. So when you add all this, you get something like 0.0664, and this is my lat closure error. So what is the departure closure error? Well, you add all the departure, and again when you add all these terms, keep the sign as it is. So this should be 184 plus 471, 541 minus 828, and when you add all these numbers, so what you get is negative of 0.1046, and that would be your departure closure error. And I saw that most of you have made mistake while adding this. I mean, you just need to add these values. That's it. So how do we find the LEOC? Again, most students have totally missed this question. So how do we find this LEOC? So LEOC is equal to, you take the square root of, so lat closure error the whole square plus departure closure error the whole square, right? And some students are confused, like, what do I do if there's a negative sign? Where a negative, a square of negative number is a positive number, right? So it doesn't matter if it is positive or negative. Okay, so what you do is you take this square root of 0.0664 square plus 0.1046 the whole square, and if you do this, what you get is 104 square plus 0.1046 the whole square, and that will give you 0.123896, right? Should be my LEOC. This is how we do it. So don't get confused with this negative sign, right? Because the square of a negative number is a positive number, right? So this is 0.1239 if I round it up to 4 decimals. And lastly, we need to find the precision, right? So how do we find the precision? So it is given by 1:, perimeter by LEOC. So what is the perimeter? If you add all the lengths, then you get the perimeter, right? The sum of the distances of the traverses is called the perimeter. So 2457.124, you divide by LEOC. So what is our LEOC? 0.1239. So 1:2. So 1:2 is the format, okay? So 2457.124, if you divide this by 0.1239, then you get 19831.50, which is my precision. So my precision would be 1:19831.5. So this is how you find the latitude and find the departure, and you find the LEOC, you find the precision, as well as you find the lat closure error and you find the departure closure error. Okay, now let us try to do the corrections on the latitude and departure that we calculated in the previous problem. So before doing that, let me illustrate the concept of the corrections that we do in the latitude and departure. So here you can see a traverse, a simple three-sided traverse. And what I've done here is I've plotted this traverse on a graph, and I've also plotted the latitude and departure of each of the traverse lines. So here for this line A and B, this is the latitude, right, which is positive, and this is the departure, which is also positive because so you're going clockwise from A like this, and you can see that north, south, east, and west. So north is positive, south is negative, east is positive, and west is negative. So these are the sign conventions. And from B we are moving towards C, so this is my departure, which is going to be positive, and from here I'm moving towards point C, so my latitude will be negative. So from C we are moving towards A, so our departure will be negative and we'll reach here, and then we have to move up to reach point A, so our latitude will be positive. So these are the sign conventions. And when I remove this traverse, what you see is a rectangle. So what we see here is a rectangle, and the unique feature of this rectangle is that its sides are parallel to this x and y axis. Okay, so we can see that this side is parallel to this x-axis and these two sides are parallel to the y-axis. So since it is a rectangle, all the corners angles are 90 degrees, and also the opposite sides are equal, right? So if this is a rectangle, if this is 20, then this should also be 20. If this is 30, then this is also 30. So the opposite sides are equal in a rectangle. However, in case of the traverse, the important property of this rectangle is that you can see that this side is positive whereas this side is negative, right? And if you see the departure, so this side is negative whereas this side is positive, like this. So what happens when we try to add all the latitude? So by adding all the latitude, I mean that you are supposed to add this side, right? Because this side is the latitude and this side is the latitude. So both sides are equal, but they have opposite signs. So this is positive, this is negative. So when you add these two sides, then you get 0, right? In the similar way, when you try to add this departure, since the two sides are equal and opposite, when you try to add these two departures, again, you get 0. Okay? So that is why, so when a traverse is free of errors, when a traverse is perfect, then the algebraic sum of all the latitude should be equal to 0, and the algebraic sum of all the departure should be equal to 0. Okay, so when you add all the latitude, then your sum should be equal to 0. Okay, and when you add all the departure, then your sum should be equal to 0. If your sum is not 0, then something is wrong. Okay. All right, so in the previous case, we did the correction for the angle. However, when we do this traverse surveying, chances are that you might also make a mistake while measuring the length. And here you can see in this simple traverse, the length of this line is too short. Let's say that you made some mistake while measuring the length, and because of that, you can see that the traverse is not closing, right? So we also need to do the correction for the length, okay? Because when one of the legs is too short, then the traverse will not close, okay? So let us see how this would impact the latitude and departure, and how we can do the correction in the latitude and departure to fix this problem, okay? Now again, I plotted this traverse on a graph, and you can see that this length is too short, because of which the traverse is not closing. So first, let us try to plot the latitude and departure, okay? So for the line AB, this is my lat, right? And this will be my departure. So for the line BC, this would be my departure, and this would be my latitude. And you can see that this latitude ends right here, because the length of this line BC is until here, right? So for the line AC, this would be my departure, and this would be my latitude. right? So let's remove that traverse. So here you can see that there is a gap in this rectangle, right? In the previous case, the rectangle completely enclosed, right? In the previous case, it was a perfect rectangle, but here you can see that there's a gap, right? And so this gap is called the latitude closure error, okay? And this gap is called the departure closure error, okay? And the whole point of doing the latitude and departure correction is to fix this thing, because you want to patch this hole, right? You want your rectangle to be like this, perfectly enclosed, and that is why we need to do the latitude and departure correction. And this thing is called the LEOC, so linear error of closure, right? So previously used this formula to calculate the LEOC. So LEOC equals to, you took the square root of this, so the lat closure error, the whole square, plus departure closure error whole square, right? You use something like this, and this is how this formula came from, because this is the lat closure error, and this is the departure closure error. And you can see that this is a right angle triangle, right? It's just a corner, it's a right angle triangle. So if I zoom in, you get something like this, right? Lat error and departure error. So this is LEOC. So what we did was we simply used the Pythagoras theorem, because it's a right angle triangle. So we use the Pythagoras theorem. H square equals to p square plus b square, and h equals to square root of p square plus b square. So let's take this h, p, and b. So this is how this formula is derived. This is how we calculate the LEOC by using the Pythagoras theorem. So how do we do the correction for the latitude and departure? So for the latitude, the correction is given by, so I want to put this negative sign, and I'll tell you why I do that. So total latitude closure error, okay, we take this and we multiply this by the length, or you can also call this as distance, and we divide this by the perimeter. Okay, this is how we do the correction for the latitude. So for the departure, what we do is, so correction equals to, we put this negative sign here, so total departure closure error, you multiply this by the length of the line and divide this by the perimeter. Okay, so this is how we do the correction. And I think you might have you might know it by now that if the so here are these three terms, okay, error and the correction. Okay, so if the error is positive, then a correction should be negative. So if the error is negative, then a correction should be positive, right? We did this in the angle. So in the same way for the latitude and departure, if the latitude error is positive, then a correction should be negative, and if your latitude error is negative, then a correction should be positive. Okay, so when you put this negative sign here, then this equation will automatically adjust for the sign of the correction. Okay, so it means that if you use this negative sign, then you don't have to change the sign manually. Okay, that is what this sign is taking care of. Okay, so if your lat error is a positive number, right? So if you multiply this by a negative sign, then your correction will be negative, right? But if your lat error is negative, right, and if you multiply this with a negative sign, so negative times negative gives you positive, so your correction would be positive, and that is what this sign is doing. So this sign is taking care of the sign of the correction. Okay, sometimes what happens is that you apply the formula, but later you forget to change the sign of the correction, and if you put this negative sign, then this formula will automatically adjust the sign of the correction. All right, so let's try to solve this problem. So again, this is the continuation of the same problem that we did in the previous topic. So here, so I have posted all the values for the latitude and departure, and also I have the latitude closure error and departure closure error. So here what we need to do is we need to find the adjustment for the latitude and departure, and then we need to find the adjusted values. Okay, so adjustment means the correction factor, whereas adjusted means the final value. Okay, the final value. So let us learn how to solve this, and again it's very easy. So to write this equation, so adjustment is given by negative of, so lat error times length divided by perimeter, right? So this is the formula for adjusting the latitude. And for departure, what you do is you take the negative of departure error times length by perimeter. Okay, the only difference is the difference between the lat and departure error, but the formula is pretty much same. Okay, so for the line AB, so what is the adjustment? So negative, right? So what is the lat error? So this is my lat error, 0.066446. So multiply this by length. So what is the length of this line? So this distance and length are the same thing. Okay, this is same as the length. So my distance is 500, and what is my perimeter? So this value is my perimeter. Okay, so if you add all the sides, right, if you have a polygon, so how would you find the perimeter of this? You add all the sides, right? So in the same manner, when you add all the distances, then this value is called the perimeter. Okay, so 2457.124. So if you do this, then you get, try to solve this, times 500 divided by 2457.124. So what I get is negative 0.013521. Okay, so I'll write this value right here since it's a latitude correction. So negative of 0.013 521. So this is how I do the adjustment for the latitude. So for the departure, what I do is, so for the departure, so negative, right? So what is the departure error? So departure error is this. So negative of minus 0.104576 times, what is the length? Is 500, and my perimeter is 2457.124. Okay, and you can see that how this negative sign will make the correction positive, right? Our error is negative, so all our corrections should be positive for the departure. So if I do this, then we get plus 6 times 500 divided by 2457.124. So this would be 0.021280. Okay, I'm taking up to 6 decimals. So this would be positive 0.021280. So this would be my adjustment for the departure for line AB. Okay, so let's do it for line BC. So follow the same process. Okay, it's similar to the one for the AB. So for BC, so my latitude adjustment would be negative of lat close error. So again, 0.066446 times 475, because the length of this line is 475. Okay, divided by perimeter is 2457.124. So if I solve this, then I get negative of 0.066446 times length divided by 2457.4. So that'll give me 0.012845. So for BC, my correction would be negative 0.012845. Okay, so all the adjustment for the latitude would be negative, because see, the error is positive, so the adjustment is negative. Error is negative, so adjustment would be positive here. Okay, so let's do the departure adjustment for BC. So for departure, it would be negative, right? Negative of negative 0.104576 times the length 475 divided by perimeter, that is 2457.124. So if I solve this again, negative times negative gives you positive, right? So you can see how that negative sign is taking care of the sign of the adjustment, times 475 divided by 2457.124, and that will give you 0.020216. So I write it right here, 0.020216. Okay, this is how I find the adjustment for the line BC. So let's try to find the adjustment for CD. So for the line CD, for the latitude, negative of lat error, right? So 0.066446 times, what is the length of CD? It's my length, 630 divided by perimeter, 2457.124. I could have solved this in Excel, but I'm just trying to show you guys how to do this. Okay, 0.066446 times 630 divided by 2457.124. So 0.017037. 0.017037. Okay, looks good to me. So negative 0.017037. Okay, this is for the latitude. So let's try this for the departure. Let's try this for the departure. So for departure, negative, right? And our departure is minus 0.104576. And what is the length? Again, 630 divided by the perimeter is 2457.124. So if you multiply this, you get a positive number, 0.104576 times 630 divided by 2457.124, 0.026813. I write it around here. It will be positive 0.026813. 26813. Do my correction. Let's do it for the one last one. Solving maths is fun, guys, so just take your time and just practice solving it. And the biggest satisfaction is, when all the equations work and when you get your answers correct. That is when you get satisfied, right, of doing this maths. So for dA, for the latitude, again, negative of 0.066446 times, so length of dA is 852 divided by perimeter, so 2457.124, so it would be negative of 0.852. You divide this by 2457.124, and that will give you a negative of 0.023 and 03, or let me round it off to 6 decimals, 023 040. So guys, you're learning one of the best mathematics in this course, and trying to develop skills in maths is always good. So let's do it for the departure. It's going to be our last one. You got to be patient, you don't need to hurry, just take your time. And departure, so for this, negative of minus 0.104576 times, again it's coming from here, departure closure error times length by the perimeter, right, 2457.124 is our perimeter. So if I do this, negative negative positive, let's try to multiply this, 0.104576 times 852, divide that by 2457.124, and that will give you 0.036261. So let me write down this value here, positive 0.036261. Okay, so I've calculated all the adjustment for the latitude and departure, and here you can see that the magic happens. See, our lat closure error is positive, so all your adjustments are negative, right? The corrections are negative, and the departure closure error is negative. That is why all the corrections are positive. Okay, so I want you guys to do this last step. So add all the latitude and departure. So I'm going to add this latitude and departure, this column here. So what happens when we add all the latitude and departure? 0.13521 plus 0.012845 and 0.017037 plus 0.023040. So guys, when I add all this latitude, what I get is I get this sum as 0.066443, right? Negative of 0.066443. And when I add all the departure, what do I get? (20216) plus 0.026813 plus 0.036261. So when I add all the departure, I get positive plus 0.104570. Okay, and you can see that when we add all the adjustment, this sum should be equal to the lat closure error. Okay, and this sum should be equal to the departure closure error. Okay, the number should be equal and the sign should be opposite, right? So here you can see that these two numbers are equal, right? And so don't worry about this last digit. Still most of our digits are are equal, right, are matching, and you don't need to worry if the last digit is kind of matching or not, but most of the digits should match. So this is positive, so your total sum of the adjustment is negative of the same number, and here it is negative, and here you are getting a positive number. Okay, so this sum should be equal to the respective latitude and departure error, and it should have a negative sign. Okay, and one important thing is that you always take at least, okay, at least 6 digit, or you can say 4 to 6 decimals. Okay, 4 to 6 decimals, but do not take just, don't take 1 or 2 decimals. Okay, so if you just take 1 or 2 decimals, then it will be hard. Okay, so do not take this 2 decimal, use at least 4 to 6 decimals would be good. Okay, so this is how you find the adjustment, and like I said, you can check if you did your work correctly or not, right? You can add all the adjustment and it should be equal to the error with an opposite sign. Okay, so we calculated all the corrections or adjustment for the latitude and departure, and here you can see the sum, right? And this the sum of the latitude correction is equal to the latitude error, but it has an opposite sign, right? And the sum of the adjustment for the departure is equal to the departure closure error, and you can see that the numbers are equal but the signs are opposite, right? So let us find the final values. So to find the adjusted value, what you do is you just take this original value, original unadjusted, right, or you can say incorrect latitude or departure, and you add the adjustments. Okay, so when I tell you to add the adjustment, make sure to keep the sign as it is. Okay, don't change the sign or don't remove the sign. Okay, keep the sign as it is. So keep the sign as it is. Okay, so let's try to find a final latitude. So take this latitude, or let me erase this. So take this latitude and add this adjustment. So 464.566286 minus 0.013521. So if we do this, then we get 464.552765. Now again, take this and subtract this. So 55.418600 minus 0.012845. Do that and you get 55.405755. Again, take this and you subtract this. So minus 321.746033 minus 0.017037. So it becomes negative of 321.76307. And finally, you take this latitude and you add the correction for the latitude. So minus 198.172.407 minus 0.023040. So you get minus 198.195.447. Okay. Now I want you guys to check your work. So add all this latitude. So your sum should be equal to 0. Okay. So let's try to add all the latitude. 464.52765 plus 55.5755 321.176.307 minus 198.195.447. So what I get here is, so I get something like 0.0000 3, right? I get something, so which is literally equal to 0. 1, 2, 3, 4, 5, 6. Yeah, I get something like this. So you can literally equal to 0. So when you find the final values of the latitude or departure, and when you add this, your sum should be equal to 0. Okay, your sum of final latitude or departure should be 0. Because if the sum is not 0, then your entire process is incorrect. Okay, so make sure that you check the sum and make sure your sum is equal to 0. So let's find the departure. So you take this and you add this value. So minus 184.873379 plus 0.021280. So you'd get something like negative 184.852099. Now take this and add this. So 471.756059 plus 0.020216 could get a positive 471.776275. So again, take this and add this. So 541.645 170 plus 0.026813. This will give you plus 541.671983. So you take this and add this. So minus 828.632425 plus 0.036261, and that would give you minus 828.596164. Now again, I'll try to add all these numbers and see the sum. So if I add all these numbers, that's 184.852099 plus 471.776275 41.671983 minus 828.596.164. So again, when I add all these numbers, I'm getting something like 0.000005, which is equal to 0. And so that is why I tell you to take the 6 decimals, because if you take 6 decimals, then you can see that all of my decimals till 5 is 0, right? And this value is 0. So when you add all the final values of the latitude, then your sum should be 0. So when you add all the departure, your sum should be equal to 0. And when they are 0, then you can make sure that your calculations are correct. Alright, so let us do this last part of the traverse computation, which is to calculate the coordinates of the points. So let me first clarify the concept of the coordinate, which is very, very easy. So let us consider a line AB, okay? So let me draw like this. Let's say this is point A, and so let's say that I have another point B, and let's say that this line has a certain azimuth, right? So what is the latitude of the line AB? Well, I told you to extend this line, right? Extend this line. So these lines meet at this point, which is a right angle triangle. So this length is called the latitude, okay? And this length is called the departure, right? So let's say the coordinate of point A is given to you, which is 1000 north and 1000 east, right? So how do we find the coordinate of point B? So let's say that the latitude of this line is plus 50, and let's say the departure is plus 60. Okay, now imagine like this. So let's say you are standing right here. So you need to go to point B from point A, right? So first you'd walk towards the north, right? You'd walk towards the north, you'd take 50 steps, and then you'd reach here, right? And from here you are gonna walk towards the east by taking 60 steps, and then finally you'll reach point B, right? This is how you're gonna go to point B from point A if you walk towards the north and then you towards the east. Now imagine there's two sets of lines. So let's consider this line in a horizontal position. So this is A and B, right? And you can see that, so the easting is 1000, and you can see that this horizontal separation is 60. So what is the length of the point B? So this is 1000 and this is 60 foot apart. So the length of this B is obviously 1060, right? And that would be the easting coordinate. So 1060 would be the easting coordinate. Okay, so let's try to find the northern coordinate. So draw this vertical line, so A and B. So this A is at 1000, right? It's at 1000, and this vertical separation is 50 foot plus 50. So what is the distance of point B? So it is 1000 plus 50, 1050, right? So the northern coordinate would be 1050 north. So hence the coordinate of B would be north and east. So how do we find the coordinates? We take the northern value and we add the latitude of this line to get the northern coordinate, and to get the easting we take the easting coordinate and we add the departure, right? This is how we can compute the coordinates of the next point if the coordinate of the starting point is given to you. So this is the concept of the coordinates. So let's try to find the coordinates of the points, and to do that we just need the coordinate of one of the points and we need the final values of the latitude and departure. Okay, so here's our figure. So the coordinate of A is given to you. So this is 1000 north and 1000 east, right? So I want you guys to sketch the latitude and departure of the lines. So for this AB, this is my latitude and this is my departure, right? So we need to find the coordinate of point B. So what you do is you take this northern and you add this northern value, and that would give you the northern coordinate, right? And you take this easting value and you add this departure to the easting value, and that would give you your easting coordinate, right? So I showed you this visually, so let's try to automate things here. So you take this northern and you add to the latitude. If you do that, then you get 1000 plus 464.552765, and that would give you 1464.5527. Okay, let me take up to 4 decimals. So this is the coordinate of point B. Okay, so how do you find the easting for B? So you take this and you add to the departure. Okay, so if you do that, then you get 1000 minus 184.852099. So this would be 815.1479. Okay, so this is how you find the easting for point B. So this would be the 1464.5527 by northern and 815.1479 easting. Okay, so again, so this is my latitude and this is my departure. So take this and add to the latitude, and that will give you the northern coordinates. So 1464.552 plus 55.405755, and this would give me 1519.9586. Okay, so uh, for the easting, take this and add to the departure. That will give you 0.1479 plus 471.776275 1286.9242. Again, you take this and you add this to the latitude. That will give you the coordinate of point D, 9.9586 minus 321.76369. That will give me 1198.1955. Then you take this and you add this to this departure. That 1286.922 plus 541.671983. And that will give me 1828.5961. And take this and you add the coordinate of A. So 1198.955 minus 198.195, and that will give me 1000. Okay, 0.000. And again, you take this and you add to this departure. And that will give you 999.9999, and this is almost equal to 1000. So you can see that we started from point A, right? So we went to point B, and then we went to point C, and then we went to point D, and again we came back to point A, right? So you started from A and you return all the way back to A, right? So the coordinate of A was 1000 and 1000, and when you return back to A, you should get 1000 and 1000. So I want you guys to check this. So if you get the coordinates of A as 1000 and 1000 here, which is equal to this one, then your calculations are correct, and this is how you find the coordinates, and this is how we can wrap up all the computations from the traverse. All right, so finally let us cover this horizontal curves, which is a bonus video. And so most of the students find this topic very challenging, but I'll make sure that all your confusions are clear. Okay, so let us get started. So to understand the concept of the horizontal curves, let's see this photo of the Horsetooth Reservoir. Right, this is Horsetooth, and you can see that we have a road that takes you all the way up to the Horsetooth, and you can see that this portion of the road is curved, right? Again, if I show you this another picture, you can see that this portion of the road is curved. Okay, so why do we design the curves while we design the road? Okay, why do we do that? So why can't we make roads like this, right? Why can't we design road like this? So if you design the road like this, then it'll be very hard for the vehicles to turn, right? Because you can see it's a very sharp turn, and chances are that vehicle which is driving at a high speed would end up ditching into the reservoir. Okay. So the purpose of this horizontal curve is to provide a smooth transition between the straight stretches of road. Okay. So if we have this straight roads and there is a change in direction, so we use these curves so that the transition is very smooth. Okay, so the horizontal curves are a part of a circle, right? Because we have different types of curves. This is also a curve, this is also curved. So what do you mean by the horizontal curve? So horizontal curves are actually the part of a circle. Okay, so when I say it's a part of a circle, so if I draw the circle, then so any arc of this circle, right, any arc of this circle is the horizontal curve. Okay, it's just a part of the circle. So let's learn about the components of the curve. So let us consider this is straight portion of the road, and we have another road. So they meet at this point. Okay, right? They meet at this point, and our goal here is to design a horizontal curve that joins this, that connects this two straight portion of the road. And the point where the two straight roads meet is called the point of intersection. Okay, it's called the point of intersection. And this angle, right, made by this preceding road to this new road is called the angle of intersection, or the intersection angle. And let us say that our curve starts from this point, right? So until here is a straight road, right? And from here, the road will start to curve. And you can see that from here, the road starts to curve. And this curve ends right here, right? You can see that the curve ends right there. So let's say the curve ends at this point, right? So we can see that a curve starts at one point and the curve ends at another point, right? So the point where the curves start is called the point of curvature. Okay, it is a point where the curve starts. And the point where the curve ends is called the point of tangency. Okay, so PC is where the curve starts and PT is a point where the curve ends. Okay. And this distance from PC to PI is called the tangent length, or T. And we have two tangent lengths, right? So if you draw the tangent along at this point, then it is what this dotted lines are representing. And again, if you draw a tangent at this line, then it is what this dotted lines are representing. And they meet at a point which is called the point of intersection. Okay. And you can see that this is the radius of the curve. And this thing, if I continue this, then it would actually form a circle, right? So the horizontal curve is a part of a circle. It's arc of the circle. And this portion is called the back tangent, and this portion is called the forward tangent. Okay, it's just the direction. And this portion is called the length of the curve. So if you measure the length along this curve path, then it is called the length of the curve. And finally, we have this distance, the horizontal distance connecting the starting point of the curve with the end point of the curve is called the long curve. Okay, so these are the basic elements of the horizontal curve. So let's learn how the stations are marked while constructing the road or during the road survey. All right, so let us consider a road like this, and we have the center line of the road, right? So how do we mark the center line of the road during the road survey? Okay, because so when we survey the road, it is different from surveying a building or surveying a property line, because the length of the road is too long, right, in thousands of foot. So how do we mark the sections of the road, or how do we mark stations on the center lines of the road so that it can be easily read by the surveyors, by the engineers, by the construction people? Okay, so here this is the starting point. Let's say this is the starting point of our road survey, or you can say this is the starting point from where you will construct a new road. Okay, and let's say that this point is at a distance of 500 foot from 0 plus 0, 0. So how do we represent this section in the drawing, or how do we represent this section in our surveying field book? So what we can do is we can write this as 5 plus 0, 0. Okay, and I'll explain you how we do that, but let's say that we mark this as 5 plus 0, 0. Now let us consider another distance. Let's say that this green line is at a distance of 1110.57 foot. Again, how do we mark this section? Well, we can write this as 11 plus 10.57, right? So 5 plus 0, 0, which is at a distance of 5,000 foot, and 11 plus 10.57, which is at a distance of 1,110.57 foot. So you can see that we mark the stations in this format, xx plus yy dot yy. So example of this is this 11 plus 10.57. So here this xx is the distance in whole 100 foot. Okay, xx is the distance in the whole 100 foot from a reference point called the station 0 plus 0, 0. Okay, so we always take the origin station, or we always take the starting point. Okay, whereas yy is the remaining value in feet. So here 11 plus 10.57 represents 11 times 100, right? Because xx is the distance in the whole 100 foot plus 10.57, and that will give you 1110.57 foot, which is the distance of this section from the starting point. Okay, this is how we mark the stations. So what is the distance of the blue line from the starting point or the origin? So if you have this station mark, then what is the distance of this section from the starting point? So what you do is you multiply this, this first digit by 100, and you add the remaining part, and that will give you 1310.57. So here's a little bit of typo here. So let me correct that. Correct this. This should be 10.57. Okay, so this is how we calculate the distance of the station point from the origin. And most of the times the starting point is not provided to you. Okay, so let's consider this section whose station point is 1 plus 33.45. So what is its distance from the origin? Okay, how do we find its distance from the origin? Well, you just take this number 1, you multiply this by 100, and you add 33.45. I don't know if you can see this or not, but yeah, so 1 times 100 plus 33.45, and it will give you 133.45. So it is the distance of this this section from the origin. So let's say our origin is somewhere here, so its distance is 133.45 foot. Now let us consider another section, 2 plus 33.45. Okay, so what is the distance between these two sections? So how do we find the distance? Well, let's say our origin is, somewhere here, 0.00. So the distance of this section is 133.45 from the origin, right? And we have another section here. So this section is at a distance of 233.45 from the origin. Now you need to find this value. So what is this value? So just subtract these two numbers, right? So just subtract these two numbers, 233.45 minus 133.45, and the distance is 100 foot, right? And what sort of distance is this? Well, this distance is the distance along the center line of the road. Okay, it is this distance. Okay, it's not this distance, or it's not like any distance, but it's the distance along the center line of the road. Okay, so this is how you find the distance between any two station points. So let's learn how to calculate different components of the horizontal curve. So our first component is the tangent length, which is this distance. So how do we find the tangent length? We use this equation called T equals to R times tan I by 2, where R is the radius and I is this intersection angle. So let's say if I is 44 degrees and R is 400 foot, then what is the value of T? So T equals to 44 degree times, let me correct this, T equals to 400, right? 400 foot times tan 44 by 2. Then make sure your calculator is set to degrees, okay? I don't want you guys to repeat the same mistakes of setting your calculator in radians. So 400 times tan 44 divided by 2 gives you 161.61 foot. This is the value of the tangent length, okay? So this is 161.61 and this value is 161.61. So the next thing is calculating the point of curvature, okay? And to find that, you'll be given this value called the PI. You'll be given the station point of the PI, and here it is 12 plus 72.18. Okay, so how do we find this PC? Well, it is very easy, right? So here this value is 12 plus 7218. So it means that this point is at a distance of 1272.18 from the origin, right? And guys, what happens if I subtract this length? So if I subtract this, won't I be getting this PC, right? So the equation of PC is PI minus T, okay? You take this PI, so here it is 1272.18, and you subtract this tangent length, and that will give you the distance of PI from the origin. So 1272.18 minus 161.61, and that will give you the distance of PC from the origin, 10.57, and we can write this as 11 plus 10.57. Okay, this is how we find the PC. So this is again from the origin, and PI minus T gives you this value, and you can write this as 11 plus 10.57, and this is how we find the station mark for the PC. So the next is the length of the curve. So how do we calculate this length of the curve? So we use this equation, L equals to I times R divided by 57.29578. So I is the intersection angle and R is the radius. So just do L equals to I is 44 degrees times radius is 400. And you divide this by 57.29578. And if you do that, 400, you divide this by 57.29578, and that will give you 307.177 foot is the length of the curve. 307.17 is the length of this curve. And this formula is derived by using these proportions, right? So L, right, divided by 2 pi r is the circumference of the circle. So L by 2 pi r equals to I, right, which is this intersection angle, and the value of the full circle is 360. And this is how we derive the equation for the length. So this is just for the reference. So next is the point of tangency. So how do we find the point of tangency? So it is calculated by using this equation PC plus L, right? So we already calculated this PC, and if we add the length of this curve, right, then we get PT, right? If we add this length of the curve like this, then we get the value of PT. So take the value of PT from the value of PC from the origin, right? And you add the length of the curve, and that would give you the value of PT. And you can write this as 14 plus 17.74. So this is how we find the point of tangency. So how do we find the long chord? So we use this equation to find the long chord. So long chord is equal to 2 times r multiplied by sine of I by 2. So here r is the radius, right? So 2 times 400 times sine 44 by 2, which is equal to 22, and that will give you 299.69. So the length of this straight line joining PC and PT is 299.69 foot. This is how you find the long chord. So now let's learn how do we actually station these points, or how do we fix these points using the total station and the serving equipment. So the design of the horizontal curve is a sophisticated process. So it is an engineering process. Usually transportation engineers are responsible for designing the horizontal curves. And the main factor here is determining the value of the radius of the curve. Okay. So let's take a simple example. Here we have 2 straight roads connecting at this point, which is known as a point of intersection, right? And so the point of intersection is known to you, and you can easily measure this angle, right? You guys are pro in using the total station now, so you can easily measure this angle, right? And based on the value of this I, you can find the tangent length, right? Which is given by r times tan I by 2. So I is known, right? So here r is not known, right? We know the I, but we don't know the value of r. So once we determine this t, so you can find the starting point of the curve, right? You can find the length of the curve, and then you can find the end of the curve. So you can actually fit a curve like this. So the most important thing here is to determine the value of the radius, right? Because we can easily measure I, but how do we determine this radius? Well, this value or the radius depends on the number of factors. So the highway engineers and the transportation engineers, they take the design speed and these different equations to determine the radius of the curve. Okay, so that is why I told you that designing the horizontal curves is an engineering process. However, your job as a surveyor or a construction manager is to use the data given by the engineer and actually lay out the curve on the field using the data. That's your job. So how do we fix the curve? Well, to fix a horizontal curve between this point PC and PT, so we have this PC here and we have this PT. So what if we fix a number of stations between PC and PT? Okay, so just think it this way. So what if we fix a number of points between PC and PT? And what if we could connect all the points? So if we can connect all these points, then we get a horizontal curve, right? So this is a big picture regarding how we actually fix the horizontal curve is by fixing the points first, and we connect all the points, we join all the points, and that points forms a curve. So here you can see that we have a number of intermediate stations between PC and PT, and the distance between these consecutive stations is called as the station interval. Okay, and this value would be provided to you, or the designer would pick some value for the station interval, and we'll use that to determine how many points should be fixed between PC and PT. So the number of points that need to be fixed between PC and PT is determined by this value known as the station interval. So let us say that we have PC and PT, and we have a number of intermediate stations within PC and PT. Okay, so how do we know how many points are we supposed to fix? So how many points, right? Because you can't fix like infinite points between PC and PT. There should be some finite number of points. And I told you that it is given by the station interval. And here, let's say the station interval is 50 foot, which means that the distance between the consecutive stations should be 50 foot. So our first point, or the PC, is at 11 plus 10.57, and our PT is 14 plus 17.74. So since our station interval is 50 foot, our first station would be at 11 plus 50. Okay, so it is either 11, right? It is either 11 and 11 plus 50, 12 plus 50. So this is how we increase the chainage by the 50 foot. Okay, so here it's already 10.57, right? It's already over 11. So our next closest station point is 11 plus 50, and that is why this first point is 11 plus 50. So what's the second station? It's very easy. So add 50. So our second station is 12. So what's the third station? 12 plus 50, right? So what's the fourth one? 13. So I'm just adding 50, okay? 50. 13 plus 50, and this is 14, right? So 14 plus 17.74 is right here, right? So we just need to end it right here. So just count the number of points. So 1, 2, 3, 4, 5, 6. So we can fix 6 stations between PC and PT. And how do you know that? We use this station interval to determine how many stations can we fit between PC and PT. So we determine the number of stations that we must fix between PC and PT using the station interval, and we got these values, right? But the question here is how do we locate these stations? Okay, so you know that the station number are these, but how do we locate this, or how do we fix these stations using a total station? So to fix this station, what we do is we use a total station and a prism. So we first set up the total station at point PC, okay, and we place the prism at PI, okay. So we sight this prism and we set this angle to 0, and we are trying to fix this 11 plus 50. Okay, we're trying to fix this. So we don't know the position of 11 plus 50 yet. That is what we are gonna determine using total station. So I want you guys to visualize it or think it this way. Okay, so what if I could turn my telescope by this angle? All right, by this angle. Okay, and what if I could measure a certain distance from this point towards this point? So let's say this is X, right? So if you know this angle, right, if you know by what angle you must turn the total station from this tangent length, and if you know this distance, then you can fix this point, right? You can fix this point, or you can fix the point for each of the station points, right? So this is a technique that we are going to use to fix those stations, okay? And this angle is called the deflection angle, okay? Whereas this is called the long chord. So this angle, the amount of angle that you should turn along this tangent length, to the point called the deflection angle, and this long chord, which is the horizontal distance between PC and this point, right? So if you know these two values, then you can fix these points, right? If you know this value, then you can fix this. So let's learn how to calculate these two values, okay? So to find the deflection angle and long chord, the first step is to find the total arc length, TAL, for this station. Okay, for this station. So what is the arc length between 11 plus 50 and 11 plus 10.57? So what do you mean by the arc length? So arc length means this length of this arc. Okay, length of this arc between PC and this station. And what you can do is you can simply subtract these two values, right? So this station is at a distance of 1150 from the origin, and this is at a distance of 1110.57 from the origin. So if we subtract these two values, then we get the length of this arc, right? We get the length of this arc between PC and this station. Let's call this A. So this length is 39.43. So this is how we find TAL, or the total arc length. So the second step is to find the total deflection angle, or TDA. So the total deflection angle is given by this equation, D times TAL. So we calculated this TAL in step 1, right? Step 1, total arc length. So what is D here? So D here is the deflection. So D is the deflection angle per foot of arc, and D is given by 90 divided by pi times R. Okay, so let's calculate the value of D. So D equals to 90 divided by pi times R. So our R is 400 foot, right? So 90 divided by pi times 400 would give you this value. And remember that it is in degrees, right? Deflection. So deflection is measured in degrees. So it is 0.0716.17. So this is in decimal degrees, or you can also write this in the DMS. So this is how we find the deflection per foot of an arc. So after you have found this D, so we calculated this TAL and we have found this. Now just plug and check the numbers. So the TDA, or the total deflection angle from PC, is given by D times TAL. So our deflection angle is this, and our TAL is this. So if you multiply these two numbers, then you get 2.82385 degrees. This is the deflection angle. So this, the value of this angle, is 2.82385 degrees. Okay. Lastly, we can find the long chord, which is the horizontal distance connecting these 2 points, right? And it is given by this equation. Long chord equals to 2 times R times sine of TDA, where R is the radius and TDA is the total deflection angle, which we calculated in step number 2. And don't worry about the formula. This will be provided to you. You just need to know how to use this formula and the different terms, right? So 2 times R times the sine of this TDA, and make sure that your calculator is set to degrees. If you do that, then you get 39.41 foot, which is the value of this long chord. So 39.41 foot is the value of this long chord. So here you can see that the value of this long chord is 39.41 foot, and this deflection angle is 2.8235 degrees. Okay, so you can use the same technique to find the long chord and the deflection angle for all the intermediate stations, right? So for this station, your deflection angle would be this angle, and your long chord would be this distance. Again, for this point, right? So a deflection angle would be with this angle, So all the deflection angle are measured from this tangent line, okay? From this tangent line. So you can visualize this as by how much angle the line joining PC to this point is deflected from this tangent line. So you can use the technique that I discussed in the previous slides to complete this table. So here our first column is this station number. So this is our starting point, and this is our end point, right? PC and PT, and these are the intermediate stations. These are the intermediate. And how do we know this station number? Well, the station interval should be given to you, and in our case it was 50 foot, and that is how we determine these stations from the station interval. The second column is the distance from 0, 0, and again it is very easy, right? So what is the distance of these stations from the origin, right? And like I said, you can convert these station numbers to the distances from the origin. Just multiply this by 100 and you add this term, right? And then you find this TAL, which is the total arc length, right? So the total arc length is the length of the arc between the station and the PC, right? So for the first one, it is 0, right? It starts from the PC. So we can visualize it like this. So this is PC, this is PI, and this is PT. And we have this curve right here, right? So the arc length is the length of arc of each of the stations measured, right? We always measure this arc length from the PC, right? So this minus this would give you this, right? So how do we get this? So you subtract this from this and you would get the total arc length for this station. So you find the arc length from with respect to this one. Okay, so always subtract this term from the original term and you would get this. And next column is the TDA, again D times TL. So after you find D, right, you can find the value of D and you multiply this with the TAL, right? So D times TAL would give you the total deflection angle, right? It's very easy. D times TAL, right? Times T times D times D times D times D times D, right? And finally, how do we find the long chord? It is given to 2R times sine of TDA. So you know the value of R, so just plug in the values of the TDA for each of these points, and if you do that, then you get the value of the long chord. So this is how you can compute this table, which is useful to lay out the stations of the horizontal curve. So finally, our figure would look something like this. So this is the total deflection angle, right? So the deflection angle is measured from this line. Okay, it's always measured from this tangent line, and so these are my deflection angle for each of these points. And my long chords are this. So these are my long chords. That is the distance between the PC and the arc length between the PC and these stations. So I measure this long chord from the PC, this, right? The value of the long chord, and these are the total deflection angle. Okay. So that's it about the horizontal curves. Make sure you review all the topics that are important for the exam too. And if you have any question, feel free to email me. All right. See you. Take care.